This is section 8.3. It deals with space. Now the key idea is fields produce forces. So the key one here is the gravitational field, and that explains star formation, explains orbits. So that is the key thing to bear in mind. Now this first central image is one from Harvard University, and they did a project on this, and what they tried to show was different types of evolution. Now we've got biological evolution, which we're quite familiar with, but they tried to use this word and they stretched it out. So here we have the evolution of particles, the evolution of the large scale structure of the universe, which involves stellar or star evolution and development, and then planets, so planets form around stars, and then chemistry, more complex chemistry begins to evolve if you've got the right amount of energy and liquids, and then biological evolution, as we've already mentioned, and then cultural evolution emerging from biological, and then they go on to speculate about the future. But this section deals with space, so that's what we're concentrating on. Now, the universe began in something called the Big Bang about 13.8 billion years ago. And, well, how do we know that? Well, there are two key pieces of evidence. One is this, CMBR, Cosmic Microwave Background Radiation, and we'll look at that in more detail. And the other is Redshift, which shows us that the galaxies are moving away from us and from each other. And we know that because of something called spectra, line spectra, which tells us about this shift. Then we're going to look at the evolution of stars. We have the analogy of life, that they're born and they die, and the color and the distribution relative to each other in something called the Hertzsprung-Russell diagram. We're going to look at that as well. Then we're going to zoom in on our own planet. We're going to think about orbits, or orbits in general, earthquakes, and also climate change. So here we have an overall introductory slide here trying to show us the three key levels in terms of structure. So uni means one, like unicycle, so there's only one universe that we know about, that we can detect, and that contains hundreds of billions of galaxies. So galaxies are islands or cities of stars. So stars aren't evenly distributed, they're clumped together in these huge balls called galaxies. They come in lots of different shapes and sizes. Now our star happens to be in a galaxy called the Milky Way. It's about 2/3 of the way out, and our star is there. We call it the Sun, although it is just the closest star, but obviously to us it seems quite different because we're so close to it. So we now have 8 planets that orbit it. We are the third one, and we are part of the first 4 rocky planets that have surfaces. The gas giants don't have conventional surfaces, so they're quite different. So zooming in even more, we've got our planet, which rotates, which gives us night and day, and we've got our relatively enormous satellite, the Moon. So three levels: universe, galaxy, and then a solar system. So a solar system is a star with planets around it, and so on. Particularly universe and galaxy shouldn't be confused. They are quite different. Now in terms of scale, here we've had to squeeze it in. Over here we've got the same thing again, but to the correct scale. So we can see here the distance between the Earth and the Moon and their relative sizes. And this beam of light is shown at the correct speed. So it takes just a little over a second for light to reach the Moon. So any other form of communication would be the same. The Sun is about 8 light minutes away, so it takes like 8 light minutes to get to us. We also have light years for greater distances, which is the distance that light travels in a year. It is not a measure of time. So let's get back to the key idea here, which is the Big Bang. Two key pieces of evidence, as we've mentioned already. So first is redshift, which tells us that the galaxies are moving away from us, and we'll look at that in more detail. And the other is cosmic background radiation, which is the afterglow of the Big Bang itself. If we could see in microwave, we would be looking at the Big Bang as it happened. And so here we have our instruments that can detect that. So what is redshift? Well, the key idea is that speed changes frequency. So the faster you move, the more you change the speed. Now this is because the movement of the galaxy, but also because space is stretching. But the key idea, as I say, to repeat, is speed changes frequency. So here we've got a galaxy, an imaginary galaxy that's green. Now if it wasn't moving, we would just see it as green. And all these other two are also sending out green light. But this one's moving at a moderate pace, so the space is stretching, and we see that as yellow light. This one's moving faster, it's further away, there's more stretching of space. So we would see that as an even longer wavelength. It's been stretched even more, and we'd see that as red light. Now, where the spectra, these dark lines come in, which we'll see in the next slide, is they allow us to work out what the true color was. How do we know that this one wasn't actually yellow, that one wasn't actually red? Well, we know where these dark lines, they're a bit like barcodes, should be if it's not moving. So this is where they should be, and this is where we perceive them to be, or our telescopes perceive them to be in these particular cases. And we can tell by how far they've moved what the speed of these galaxies are. So here we have the more detailed explanation of where these dark lines, these spectra, come from. So here we've got a normal white light, and all the colours are represented, a continuous spectrum. Here we've got the same starting point, but here we've got a cloud, and this cloud is absorbing a very particular frequency, and so it's not reaching our telescope. So we see this dark line. Now in reverse, if this cloud is excited and given energy, we have the emission of the exact opposite. So you can see these are negative images of each other. So we can do this in the lab, and we can establish exactly what chemicals give barcodes. And we can see that on this slide. So this is the periodic table, or a list of elements, and with rather beautiful patterns of lines, but they are also very precise and completely unique, and so enormously useful in establishing what chemical we're looking at. So here then we have a couple of different images, or three. The first one here is a composite of all these little dots represent galaxies, and the color here is their redshifts. So you can see that as we go out further towards the edge of the universe, they are more redshifted, these oranges and yellows and greens here. So it's a very visual way of representing the expanding universe. And we've got a key down here, and we can see these increasing redshifts. So this is an animation here. It's a bit basic, but it gives you an idea of what's happening. So these are the galaxies moving away from each other. Now what Edwin Hubble did is he looked at these redshifts, and he put them on a graph. This is something called a mega parsec, which is a measurement of distance, and this is speed. So he put these on a graph, and he saw the further away they are, the faster they're moving. So he was able to visualize this at the bottom, and our modern instruments are rendering it in a slightly different way. But galaxies are moving away from us, and the further away they are, the faster they're moving, hence the idea of expansion. Now, expansion doesn't necessarily imply a Big Bang. Some people thought a steady state, maybe it's just always been expanding. But in the 60s, we found something called cosmic background radiation. We found wherever we looked in space, there was this completely consistent background hum from all possible directions. And as we've already said, that we now understand to be the afterglow of the Big Bang itself. And here we have our progressively more detailed versions of this. These are all from space satellites, creating these incredibly accurate maps. Now the differences here between the blue and the red are a few thousandths of a degree, so it really is incredibly consistent. So moving on then to star life cycles, as we said at the beginning, key idea is fields create forces, so gravitational field being the key one. So over here we have a cloud of dust in space, and it's all attracting each other, so it begins to pull itself together, and at a certain point it becomes so dense that we get these black arrows, and that represents the beginning of fusion. So at about 10 million degrees, the hydrogen, mostly hydrogen, begins to fuse, create a huge amount of energy, and it begins to push back. But to begin with, it's not as strong as gravity, but eventually it is, and we get this stable state here where the two exactly balance out, and that's the state of our current star. Now, this shows us a summary of the different life paths of different stars. As we said, well, nebula is just a posh word for a cloud of gas, and our sun is an average star, and this is the state it's in at the moment, this balance between the two. Now, as the mass is used up, eventually fusion will win, the expansive forces will win for a while at least, and expand the star out. However, gravity always wins in the end, and after a while it gets so big that it can't hold on to its outer gases, and finally they drift off and we're left with a white dwarf. Now, if a star is more massive than our star, about 4 or 5 times more massive, we have a different story. It actually lives less long, it burns more furiously. Something similar happens in that we get a red giant, but this can go supernova, so there's this sudden massive explosion. Lots of chemicals are created, new elements created, but again gravity wins in the end, and it can either produce a neutron star, which is incredibly dense, or if it's more massive still, it produces a black hole. So a black hole is not a hole, but it certainly is black. It's so strong in its gravity that not even light can escape. So this is the Hertzsprung-Russell diagram. It places on one image a huge variety of information, but basically we've got stars being born here, or fairly young stars, and they are very hot, blue, which we'll come on to in a second, and as they age they cool and they get redder and redder. Now, as we've already said, there's this sudden expansion. We can see our timeline here. They become giants, and eventually they become white dwarfs over here. But a huge amount of information here. We can see the luminosity, which is the power, the amount of energy. It goes down over its lifetime, as you can imagine, but then this new source of energy is tapped into, so it goes up again, and then it sort of has a final big flare out in essence. So as we mentioned earlier, the colors tell us something about the temperature. Now, we humans associate blue with cold because of our physiology, but in stars it's the opposite. So a red star isn't cold, but I've started with the word hot, then I've gone very hot, and I've gone super hot to try and get us in the right ballpark. But you can see that this peak moves along. So this is the peak intensity. So here the peak is actually outside the visible, so it's in the infrared. Here the peak is shifted along, so these are higher frequencies, higher energy, and finally here it's in the ultraviolet. But here still a lot more blue light coming from these super hot gases. So in summary, hotter equals bluer. Here we can see two key types of orbit. Firstly, on the left here we have the polar orbit. Now, as its name suggests, it goes over the poles. The advantage of this kind of orbit is that it gets to see the whole planet because the planet is spinning underneath it. So it's very useful for weather and other applications. Now, on the right side here, we have one key orbit here, which is the geostationary orbit. Now, as you can see, it remains above the same part of the world, the United States in this case. Another way of saying it is that its orbital time is 24 hours, which obviously matches the orbital time of the spinning planet. Now, both these are artificial satellites. We also have one natural satellite, the Moon. Other planets have, in many cases, more, up to 60 or 70 satellites or moons. Now, geostationary orbit, as we've said, has the advantage that it doesn't move relative to the planet, which means you don't have to track it. So it's extremely useful for communication purposes. So here we have something very similar to what we saw in a previous video, but here there's no direct connection, but the point the board wants you to understand is the same, in that you can have a change in velocity without a change in speed. So the speed of this satellite is constant, but because its direction is changing, its velocity is changing, because velocity is made up of speed and direction. So we're familiar with speed change equaling velocity change, we're less familiar with direction change equaling velocity change, but it's nonetheless a cause of velocity. This slide illustrates the relationship between the strength of gravity, which gets weaker as we go away from the planet, and the speed of orbit. Now, these two things aren't necessarily linked because they need to be balanced. So here on a low orbit, you need to be going very quickly to counteract or to balance this strong gravitational pull. The satellite wants to carry on in a straight line. Newton's law, first law, tells us that. There's a force inwards, its weight in this case, that is causing it to change its direction constantly, or travel in a circle, or have an orbit. They're all equivalent ways of saying the same thing. Now here a bit further out, we happen to have the geostationary orbit here again, but it's true of any orbit. It's going to be going slower here, but the physics is exactly the same. It's being balanced, and it's also true of the natural satellite, the Moon, with a much longer orbital time. It's much further out. Now over here we can see this denser band here. All these dots are enlarged satellites to give us some idea of the number of satellites that orbit the Earth. But this denser ring here shows the geostationary satellites, and it shows us how useful they are because they are so numerous. So this point is about the energy balance between the Sun and the Earth. So we rely on the Sun, we need to trap its energy, and without the greenhouse effect we'd be about 20 degrees cooler, but we humans are releasing coal, which was trapped many hundreds of millions of years ago, and we're pumping it into the atmosphere, and that's causing global warming or climate change. So regionally the climate can change. It doesn't mean every single place is going to get warmer. So the climate change deniers will try and confuse us and talk about the natural cycles and so on. Now there are natural causes of temperature change, but they're on incredibly long cycles, 100,000 years, and even the shorter ones, such as sun activity, are actually at minimums now. So the heat intensity does vary, but not as quickly as we're seeing. Volcanoes are pretty steady, as is respiration, but the man-made effects, burning fossil fuel and deforestation, which is also involves a lot of burning, have increased markedly. We could go back to 1850, the start of the, we can go back a little bit further than this, but this is where my graph goes from. So, you know, a very strong correlation, and there's a huge amount of science to back this up. Moving on now to earthquakes, and before we get onto that, we need to understand the difference between primary and longitudinal, which again we came across in a previous video. But the key point here is that longitudinal waves here, that the vibration is parallel to the motion, can travel through liquids, as you can see here. Secondary waves are transverse waves, so they will travel through solids, but they won't travel through liquids. So that's the key difference to bear in mind. So when we have a look at this next slide here, we see here on the left we've got our earthquake and the waves spreading throughout the planet, and the primary waves will travel through the liquid core, but the secondary ones won't, and that gives us this shadow effectively. So these two seismometers will pick up nothing, and this gives us information as to what the center of the core of the Earth is like at all.